Hello everyone, welcome to another video lesson. In this video lesson, we'll look at how to solve problems on testing of hypothesis using the RStudio software. If you can recall, we had already posted a video lesson on fundamentals of testing of hypothesis for large samples. We discussed a few problems there. Those problems were solved analytically. Given the link to that video lesson in the description, you can check that out. In today's lesson, we'll focus on how to solve such problems using the RStudio software. To give you a recap, the general procedure of hypothesis testing depended on finding the value of the test statistic and its comparison with the critical value. We decided on the critical value and the critical region and the confidence interval, and that helped us identify how extreme can the test statistic be, or how far away can the test statistic be plotted on the graph. If the value falls in the confidence interval, we accepted the null hypothesis. The value falls in the critical region, we rejected the null hypothesis. We saw that for a two-tailed test, the critical region is at the two extremes. For a one-tailed test, it is towards the left extreme or the right extreme. Now, these decisions are based on the value of the test statistic and the critical value for the corresponding test. However, there is another approach possible based on the p-value of the corresponding test statistic. We'll focus on this p-value because when it comes to using software to decide whether to reject or accept the null hypothesis, using the p-value is a more convenient choice. Now, how is this done, or what is the p-value? That's the objective of this video lesson. So we assume that the null hypothesis is true and we calculate the value of the test statistic. Now let's assume that the value of the statistic is very extreme. It's either too large or too small, and we call it as t. Now, the p-value of the test is the probability of obtaining a value t dash, which is more extreme than the value which we just calculated. So, what is the chance that such an extreme value is obtained as a result? What is the probability of this happening? This is defined as the p-value, which is the probability. Now, this probability is compared with the significance level. We already learned what is the significance level, or the level of significance. This is denoted by alpha, and it defines the probability that such an extreme value will exist, and as a result, the null hypothesis will be rejected. You can recall that alpha is the probability that H naught will be rejected. So we compare the p-value and alpha. Now, the decision is made as follows. If p-value is greater than alpha, we accept the null hypothesis, which implies there is a greater probability for the null hypothesis to be accepted because p is greater than alpha, the probability that we must reject H naught. On the other hand, if the p-value is less than alpha, then the probability that we accept the null hypothesis is very less compared with the probability of rejecting the null hypothesis. Therefore, we reject the null hypothesis. So this is in fact the direct opposite of what we did with the critical value. The critical value, if the calculated value is less than the critical value, we accept it, and if it's greater than the critical value, we reject it. This is the exact diametric opposite. So this is what we follow to establish a familiarity with the concept of p-value. I've included a couple of problems. One of them is already is one of them. We've discussed one of them already. Let's just have a look at them. A sample of 49 observations has a sample average of 5.5, and we're asked to examine the claim that this sample is collected from a normally distributed population with an average of 5 and a standard deviation of 1.5 at 5% level of significance. So this is a classic problem of a large sample with 49 observations recording an average of 5.5. and we are comparing this with the population mean at 5. So the null hypothesis and the alternate hypothesis are easily noted. This is H naught, this is HA, and therefore we have a two-tailed test. The sample size is at 49. The sample average is at 5.5. The population standard deviation is at 1.5, and the level of significance is at 0.05. Once we know all this, we know how to calculate the value of the test statistic that comes down to 2.33. Now, in the previous method, we just compared this 2.33 with the critical value for a two-tailed test of a large sample at 5% level of significance. We know that is 1.96. We've already discussed this at length. So comparing, we see the 2.33 is greater than 1.96. Therefore, we reject H naught. This is what we have done so far. For the method based on the p-value, we determine the probability that the test statistic takes a value that is either greater than 2.33 or less than minus 2.33. This is because we do a two-tailed test. So we reject the hypothesis if the value is too large or too small. But it is enough if we find one of these two. In other words, it is enough if I find the probability that Z is greater than 2.33 by virtue of the symmetry of the normal distribution. So we do that by referring the chart. We locate 2.33 in the chart. The area between 0 and 2.33 comes down to 0.4901, which means the area to the right of 2.33 is 0.0099. By virtue of symmetry, the area to the left of minus 2.33 is also 0.0099. Therefore, we can determine the p-value by adding these two areas or probabilities to get the value as 0.0198. In other words, the probability that it is greater than 2.33 and the probability that it is less than minus 2.33 are added together to get the value of p-value as 0.0198. Now, when we compare this with alpha, we see that the p-value is less than alpha value. And hence, by the rule that we have learned before, we reject the null hypothesis. That is, we conclude that there is no sufficient evidence to support the statement that the population mean is 5. The next example is the one we have already seen when we discussed the analytical solution of hypothesis on based on large samples. It goes on like this. The average height of male students in the city is known to be 185 centimeter. We compare to analyze this claim. We consider a sample of 121 having an average of 183, and the population standard deviation is 10 centimeter. We find that if this claim is accepted at 1% level of significance. So the null hypothesis is that the average is greater than or equal to 185. The alternate hypothesis is that the average is less than 185. So we have the sample average at 183, the sample size at 121, the standard deviation at 10, the population mean at 185, the level of significance at 0.01. Substituting these in the formula for the test statistic, we find the calculated value 2.2. Now, for a critical value based approach, we compare this with the critical value of the test statistic for a left tail test at alpha is equal to 0.01. The value comes down to 2.33, and comparing, we see that the calculated value is less than the critical value, and therefore H naught must be accepted. Now, we'll discuss how to do the same thing with the p-value based approach. We determine the probability that uh, the test statistics take a value greater than 2.2. Once again, we use a normal distribution chart, and we find that the area to the right of 2.2 comes down to 0.0139. So since this is 0.0139, the value, the p-value that we wish to find is available. The p-value is at 0.0139, and we compare this with the level of significance at alpha is equal to 0.01. So the p-value is at 0.0139, alpha value is at 0.01. We see that the p-value is marginally greater than alpha, but still it is greater nonetheless. And since it is greater by the decision making convention that we follow, H naught must be accepted. So that is sufficient evidence to support the null hypothesis. Now, having discussed The analytical approach about solving a hypothesis problem based on the p-value. Now we are ready to find out how to do the same thing using the R Studio. Now, to use the R Studio and test hypothesis based on large samples or whatever sample it is, we need to install this package called as Basic Statistics and Data Analysis. It's available in the R Studio's updated version by the name of BSDA. So the bottom right panel of the R Studio console, we find that there is an option to install this package. So we click this and we install. I've already installed this package for you. Now we'll have a look at solving a few problems based on the hypothesis testing using RStudio. Now, the general way of solving problems will be this. We will define a function to calculate the p-value. The reason why RStudio uses p-value is that for test statistics based on normal distribution, finding the p-value is very easy because we always have the chart at our disposal. So finding the area to the right is pretty simple. But if you can recall, doing the same thing for chi-square MF is not that easy. That is why calculating the p-value is done using a software. So R Studio uses a program or a function for itself to find the p-value. And that is why textbooks, which are written by foreign authors, do not usually use charts. They use the p-value for the decision, for making the decision regarding the acceptance and rejection of the null hypothesis. So this function which calculates the p-value differs based on the test statistic. Now, for large samples, we use the function called z-test, z.test or z.test based on your convention. This z.test function uses a few arguments. Argument 1, it calculates the data based on the sample data. We call it as x. Argument 2, we specify the population average. Argument 3, we specify the population standard deviation. Argument 4, we define whether the test is two-sided or greater or less. So we define what kind of a test we are performing. And argument number 5 is the confidence level. Now we know how the confidence level is calculated. Confidence level is 1 minus the level of significance. So we pass these 5 arguments into the function called z-test, and that will help us generate the p-value. To generate the p-value, we use this another function. We denote it by value $p dot value that returns the p-value corresponding to the test statistic. Now, once we get these two, we can use these to compare and arrive at the conclusion whether to accept or reject the null hypothesis. We'll go into the first problem next. Okay, the first problem goes on like this. Sample of 100 students is taken from a large population. The mean height of the students in the sample is 159 centimeters, and we consider if we can accept the claim that the mean height is 164 and the SG is 10 centimeter at 5% level of significance. So we define the null and alternate hypothesis for this problem. It's pretty simple. And after this, we call the package using the library function. So like I told you before, we need to install the BSDA package. Having installed the package, we call the package using the library function. And we define the sample data. The average is at 159, the SG is at 10, and the N is at 100. And we compare this with the population data, and this is where we use the z.test function. This line here, we'll use the z.test function. It takes as argument the sample data, the population mean, the population SD, and the alternate hypothesis along with the confidence level. Now, since 5% is the level of significance, we have the confidence level at 95%, is at 0.95. So this function z.test calculates the z-value, and the corresponding p-value is calculated in the next step. Z-value $p-value returns the p-value corresponding to the test statistic. And then we define the algorithm to decide whether to accept or reject the null hypothesis. Like we discussed before, if the p-value is less than alpha, we reject, otherwise we accept. Now, having written the code, now let's try and execute the same using the RStudio function. I have called the package using the library function, and now let's run this chunk and find out what the result is. So this should return an answer. Yes, we observe that the p-value is 0.4204 10 to the power of minus 5. So it is 0.000. And comparing this with the alpha, we see that it is less than alpha, and hence we reject the null hypothesis. So this helps us decide in a very quick manner. The second problem again is about the breaking strength of cables. We define the null and alternate hypothesis. Uh, we are supposed to check the claim that the breaking strength has increased. So HA will be defined as mu greater than 1600, and H naught will be defined as mu less than or equal to 1600. Having defined these two statements, we call the package using the library function. We define the data of the sample, and we then have the z.test function, which calculates a test statistic value. This problem is again is that 1% level of significance, which means our confidence level should be at 0.99. It's not at 0.95, it is at 0.99. And then we calculate the p-value corresponding to the test statistic, and we define the decision process based on the comparison between p-value and alpha. Having done the code, let's find out how this code gets executed in RStudio. So we have the level of significance at 1%, which means the confidence level is at 0.99. Make the correction. And we have defined the sample data. We have defined the z.test function. We have defined the decision making process. Now let's execute this and find out what the answer is. Once again, we believe that we have 0. We have 2.73 times 10 to the power of minus 7, which is again very small value compared to the value of alpha. We have to change this part also. P-value is less than 0.01. We reject the null hypothesis. We run the program again. The result is for us to check. In both cases, we see that the null hypothesis must be rejected. So the conclusion that we arrive is to reject the null hypothesis. The third problem is about a different kind of an alternate hypothesis, which says the average height is less than 185. So HA is mu less than 185, and H naught is mu greater than or equal to 185. We define the sample data, and we define the z.test function, which calculates the test statistic value. The corresponding p-value is determined, and based on the comparison, we arrive at the decision. Having defined all data here, I've already written the code. You can directly run this chunk and identify the decision. We have run the code here. The result is we fail to reject the null hypothesis. Or in other words, the null hypothesis cannot be rejected, and therefore we accept the null hypothesis. H naught will be accepted because the value we obtained, the p-value is at 0.13. Comparing this with the p-value at 0.01, it's obvious that 0.13 is greater than 0.01, and hence the null hypothesis must be accepted. All right, we have one last problem in the large samples. The next problem will check if there is significant difference between two sample averages. The amount of a certain trace element in blood is known to vary with an ST of 14.1 parts per million for male donors, 9.5 parts per million for female donors. Random sample of sizes 75 and 50 gave us averages of 28 and 33 parts per million. What is the likelihood that the population means are the same for men and women? So we'll define the null hypothesis. There is no difference between the means. There is an alternate hypothesis which says that we have a significant difference between the means. Now, having defined the null and alternate hypothesis, we have called the function, we have called the package library of using the library of BSDA function. We've defined the data for the two samples, 75 and 50 being the sizes, averages being 28 and 33. The standard deviations are also given, and based on that, we find out the value of the test statistic using the z.test function, and we define the procedure to make the decision. Having made the decision, having defined all this, we can run this code. Let's find out what the result says using R Studio. So we have called the package using the library of BSDA function, and we observe that the p-value is at 0.019. And since this is tested at 5% level of significance, we see that the p-value is less than 0.05, and hence we are supposed to reject the null hypothesis. We claim that there is no sufficient evidence to say that the two means are almost equal. So there is a large difference, and therefore we reject the null hypothesis. That's how we have discussed problems based on large samples. In each case, we have defined the corresponding uh, uh, function in R Studio to calculate the test statistic and its p-value. We have also seen how the results pan out using the R Studio software. In the next video lesson, we'll discuss the same for the chi-square test shortly.